This is a video on three kinds of objects studied in vector calculus. When you do integrals in vector calculus, one of the things you do is you do line integrals over vector fields. You do line integrals of vector fields. And really shouldn't use the term line integral. It really should be curve integral, because when you do a line integral, the region that you integrate over is a curve. What is a curve? A curve is a line, almost a line, except that instead of a line which has to be straight, a curve is allowed to be wavy. It's allowed to be not perfectly straight. So let's take, for instance, this power cable, okay, for a DSL modem. And if we just ignore sort of this little block over here, and of course this charger part, just imagine this cord, but thinner, and if you just move it around like this, you just fix, freeze how it looks, that's a curve. Another example of a curve is, for instance, this slinky. Again, not when it's all stuck together like this, but let's think of the curve over here, right? So see the amount of the curve that you see on the screen once the slinky stops moving. Once we fix the location of all the points on the slinky, that is an example of a curve. So a curve is a one-dimensional thing because it's a line, really, that's been deformed a little bit. And then the next thing that we look at are two-dimensional things which are wavy. So a two-dimensional flat thing, completely straight and completely flat, that's a surface, right? So a surface is a plane, except that a plane is a special type of surface in that it's flat. So for instance, if you take a sheet of paper and you just make sure that it's completely flat, that's a surface, but you're allowed to take the paper and allow it to bend in places, right? So just kind of tweak the shape a little bit, like that, for instance, and that is also a surface. Now we have several other examples of surfaces. For instance, this. The plastic that makes up this bottle is a surface, and it's also an oriented surface. Let me remove the cap to this coffee that I'm drinking right now, and I won't turn it because otherwise it will spill on my camera. But this is an example of another surface, and if I remove this sleeve, this is also a surface. Okay. I have another surface here just by looking at the packaging of the Pringles, and this time I'm including the top. Okay, so I haven't opened this can of Pringles, and if you just look at all the packaging but not the chips inside, that's an example of a surface. One final example of a surface is the packaging of this Play-Doh. Right? If I remove the cap, if I remove the lid, is this child-proof? Okay. If I remove the lid, then this is a different surface. And again, I'm just talking about the yellow packaging, right? So one surface when you have this, and I'm going to change the surface by removing the top, and here's another surface. Okay. So that surfaces are all examples of two-dimensional things because there are planes just allowed to be wavy. Finally, we have three-dimensional things, and those are called solids. So for example, if I open up the Play-Doh and make sure that there's no holes inside it, if I compact the Play-Doh up, press it, then this is an example of a solid. So a very classic example of a solid is going to be a solid ball, right? Take the unit sphere and fill it on the inside. Oh, and I bring up a very good point, is that very often when we talk about these things in English, there's a little ambiguity whether we're talking about an object for the outside piece or the filled-in part. So when we talk about a sphere, for instance, in math, a sphere is a surface. What we do is we look at just the outside part, and when we talk about a ball, we actually fill in the inside. Okay. This brings up another very important point, is that these objects are all related to each other by boundaries. So we have three-dimensional solids, we have two-dimensional surfaces, such as this, and we have over here one-dimensional curve. And the point is that when you look at the boundary of a three-dimensional region, when you look at the boundary of a solid, you'll get a surface, a two-dimensional thing. When you take a surface, which is a two-dimensional thing, and look at its boundary, you'll get a one-dimensional thing, a curve. All right? So let's make sure that we understand what boundary is. So let's take this three-dimensional object. Right? The boundary of a solid is, imagine that you are stuck inside, or a bug is stuck inside this thing, right? And it can't breathe. Where is the surface? Where is the boundary of this solid region? It's a surface. That we already said what it was, but which surface is it? Imagine you're a bug, and since you can't breathe, you need to try to crawl in certain directions, right? So crawl from being in the middle of the solid object, crawl around, and at the first point you can breathe, any such point when you crawl around, the first place where you can breathe and get your first breath of oxygen, that is a point on the boundary. So the boundary of this solid region is actually all the parts of the Play-Doh that we can see. Now inside, we know that there's more Play-Doh in here, but that's the part that, at least before I broke it up, we couldn't see. Okay, if I were to change this solid, we could talk about a solid cube if I just try to shape this thing, right? Okay, you get the idea. I haven't done a great job with this. But if we take a solid, a filled-in cube, a heavy cube, then the boundary, if you're a bug stuck inside this cube-shaped solid, then the boundary are going to be these 6 squares around the outside. Right? So this time the boundary has 6 sort of separate equations, one for each of the 6 squares. And so the boundary of a solid cube is, if you want to call it this, the hollow cube, and the hollow cube is a surface made up of 6 simpler surfaces, namely 6 filled-in squares. All right, now when we look at surfaces, like the container for the Play-Doh, if we just look at the packaging, this is an example of a surface. And what is the boundary of a surface? Well, remember that a surface could have been made out of paper, right? This was an example of a surface, and this is perhaps the right example of a surface to understand what a boundary is. So let's go back here, and imagine you have Play-Doh. This container, the boundary of a surface is, imagine that the surface is made out of paper, and the boundary is all of the places where you could potentially get a paper cut. So if this were made out, if this surface, this yellow surface, were made out of paper, some people would say that the boundary is out here, but this is somehow this side lateral part. It's sort of maybe English to say that this would be the boundary, but mathematically the boundary, the places where you get a paper cut if this is made out of paper, is really this rim right here. Right? So this is the boundary. Let's take this coffee cup as well. So where you drink the coffee out of, right around here at this top, that's the boundary. This down here is not a boundary. Well, maybe for this it's sort of weird, but imagine that there's no extra thing up here, it's completely flat. Then you wouldn't get a paper cut. Yeah, it's sort of a sharper edge, but it's not an exposed edge of the paper. Okay? For the sleeve for the coffee thing, this surface has 2 boundaries. They're 2 separate components, 2 boundary pieces which are not connected to each other. If this is made out of paper, and in fact it is, I could get a paper cut up here, and if I turn it upside down, down here. So the boundary of this surface is 2 separate circles. If you were to use Stokes' theorem and you needed to compute curl of a vector field over the surface, when you convert it to a line integral, you'd actually get then 2 line integrals, a sum of 2 line integrals, simply because there's 2 separate circles that you'd have to separately parameterize. Right? And so what are the boundaries in all of these cases? Let's maybe go back here. The boundary of a surface was this rim over here, and what kind of object is that? That's the one-dimensional curve. Take this power cable here and just put it up on top here.